Hi, this is Ms. Delosier, and these are the notes on acceleration. So, let's look at what acceleration is. Acceleration is a change in the velocity over time of an object. So, it's the change in how fast an object is going with direction over time. So that's really it. So if I'm going 2 meters per second and then I'm going 5 meters per second and that takes me 35 seconds, we would say that I've accelerated because I sped up. It can also mean that you've changed your direction, because if you think about it, when you have a velocity, velocity indicates both the speed and the direction. It's both the magnitude and the direction. So you have to have a number and a direction. So if I'm going 55 miles per hour north, and then I turn around and I'm going 55 miles per hour south, that would indicate that I've also had a change in my velocity. So I would call that technically an acceleration too. And we'll talk more about that when we do our graphs. But for now, let's just do a little bit of review. So let's say that I have a car and it's on a hill, and at the bottom of the hill, we know that it's going to be going pretty fast. So where is the car faster? And so right now I want to know, is it faster at the top, or is it going to be faster at the bottom? And I think that you guys have all seen from the lab that it's slow at the top and it's fast at the bottom. So let's look at some sample data. Let's say that the car is going 0 and 0 at the top, and then after 1 second it's going 10, and then after 2 seconds it's going 20. So the car is increasing its velocity at 10 meters per second every second. So what we would do is we would say that that is 10 meters per second, or 10 meters per second squared. And that sounds pretty confusing, but you can see that if my velocity is 10 meters per second and then I divide that by seconds, then I have an extra second there. So basically just keep it straight in your head like this. If it just says meters per second, that's giving you a speed or a velocity. If it says meters per second squared, that's an acceleration. So let's go ahead and let's look at how we could calculate acceleration. So we're going to calculate acceleration using a formula where it says acceleration is equal to the final velocity, that's how fast it's going at the end, minus the initial velocity, that's how fast it was going at the beginning, divided by the change in time. And we write that as AVF minus VI divided by delta t. Remember, the triangle is delta, and that just means change in. So let me give you an example. Let's say that it took me 5 minutes to speed up from 0 to 10, right? What's my total change in time? 5 minutes. So delta t for that would be 5. And we're going to do a sample problem, so if that doesn't make sense to you, hopefully it will at the end of the problem. So a boat is sailing at 1 meter per second. It increases to 4 meters per second in 3 seconds. What is the acceleration? So the first thing I need to do is I need to go ahead and I need to make a list of my variables. So I'm going to have A equals, VF equals, VI equals, and T equals. And I'm going to fill in what I know. I know that at the beginning I'm going 1 meter per second. And then I know that I speed up to 4 meters per second. And I know that that takes me 3 seconds. So then all I'm going to do is plug those numbers in. So I'm going to have acceleration equals 4 meters per second minus 1 meters per second divided by 3. So that's really just going to be 4 minus 1 over 3. 4 minus 1 is 3 divided by 3 equals 1. So my acceleration is going to be 1 meter per second squared. And hopefully that calculation makes sense to you. The formula is something that you should be comfortable with, but whenever you're going to do this, you're going to have access to a formula chart. So just make sure you know how to use it, and I'm not really concerned about you memorizing it. So we're going to go ahead and we're going to review a little bit. So average acceleration is delta V divided by delta T, and that just means the change in, triangle means delta, change in velocity over change in time. So that's VF minus VI divided by TF minus TI. If you wanted to know specifically just the time final minus time initial, that's just your time. How long did it take? That's pretty easy. So, but what if instead of me calculating the acceleration, I wanted to actually calculate the displacement? So you remember displacement is how far it was from where I started to where it ended. So let's say I was accelerating at a rate of 10 meters per second for 5 seconds, and I wanted to know how far I'd gone, right? There's a formula for that, and I'm not going to make you solve anything with it right away, but I want you to see the formula so you're not freaked out. Here's the formula. The change in d, distance, the change in distance is equal to the initial velocity times time, so how fast I'm going at the beginning for how long I'm going that fast, plus 1/2 a times delta t squared. And that's a super, super complicated formula, so we're going to label it. That's your initial velocity. That's easy, right? And that's time, just plain old time. That's all that really means is how long did it take. And that's your acceleration. So you could go ahead and find out what is the total displacement that you went. Now this formula is way, way, way more complicated than you're almost ever going to have to use. Normally what's going to happen is that your initial velocity is going to be stopped. Your object will be at rest. So if your object starts at VI equals 0, meaning you're stopped, so it says like my car starts from stop, so like I'm parked and then I start going, how far did I go, right? Then we would just write that as, we would just write that as the change in distance is equal to 1/2 at squared, or just d equals 1/2 at squared. And that's how we normally write that. So like if I said I'm accelerated at 9.8 meters per second squared and I do that for 5 seconds, how far did I go? You would just plug that in. So a would be 9.8, t would be 5, and you would just solve for d. And that's a little easier to solve for. But if I did have an initial speed, you would have to use the big complicated purple equation. So let's go ahead and look at graphs. So acceleration graphs. Acceleration graphs sometimes scare people, and I don't think that they should because they're normally pretty easy once you actually look at them. An acceleration graph, since acceleration is just going to be the change in velocity over the change in time, you're going to basically look at any graph that shows velocity on your y-axis versus time on your x-axis. The slope is going to give you acceleration. So here's what that means. It means if I have a graph where I've got time on the x and I've got velocity on the y, I'm going to draw a little graph real quick. Here's what happens. On that first section, part A, part B, part C, on that first section, part A, I'm speeding up. I'm just increasing my velocity. That's all that means. Part B, it's flat, or it's supposed to be flat, but I didn't draw it very well. So in part B, my velocity starts and stops at the same level. So my velocity is constant at, say that's 5 meters per second. So if my velocity is constant, that means that I have a constant velocity and my acceleration is 0 because I'm not speeding up or slowing down, right? And then in part C, it looks like I'm actually going to decreasing velocity. Now, what does that mean? It means that I had a positive velocity and I'm going back to a velocity of 0. So I'm stopping there. So I'm speeding up, I'm going to constant speed, and then I'm braking. That's all that means in that graph. So let's look at interpreting another graph. And we're actually going to start with a distance versus time graph. And that actually would show the speed of an object, because remember, if I have distance on the y-axis over time on the x-axis, that's speed, right? And then I'm going to look at a velocity versus time graph, and I'm going to graph the same object doing the same thing. So hang on. So if you look here, my object is going to go ahead and I'm going to have a steep slope, so that means that I was going really fast, right? And then there, I'm not increasing my distance at all. My distance is constant. That means my velocity equals 0. When my velocity equals 0, that means I'm stopped. It just means I'm standing in place or I'm parked. And that green line, I'm going slower, and I'm also going back to the starting line. So I'm slower and I'm going in the negative direction. Now, if you look here, this is going to line up. On the blue line, that's the steepest, and that's a positive. I'm increasing my speed, right? I'm going at a constant velocity. I didn't mean that I'm increasing my speed. I'm not. I'm going at a constant velocity, and it's positive. So I'm going to go and draw a straight, flat line, constant velocity. My velocity is the same number, so that's flat. and it's positive. And that's pretty complicated, but let's pretend that my velocity here is 3 meters per second, right? So this would be, this blue line at the bottom would just be 3 meters per second. Then here, the purple line, my velocity equals 0. So what I need to do is I need to drop the line back down, and I need to draw the purple line right on the 0. So let's do that. So it's kind of hard to see, but the purple line's right on the black axes at 0. And then the green line, I'm going slower and in the negative direction. So I'm going negative, so I'm going to have a line that is not as big of a velocity. So it's going to be smaller, but it's going to be negative. So it's going to be below the line. So like that. And we're going to practice these quite a bit. So you can refer back to this, and there's a link with some more practice problems on the website too.